Okay, so today we want to look at part two of our discussion of dynamic programming, that is infinite horizon optimization problems under certainty, right? There's no randomness to these types of problems. So what did we accomplish in the last class? We set up kind of the generic version of these infinite horizon optimization problems, defined all of the relevant notation, differences between states and controls, payoff functions, constraint correspondence, etc. Got to know what those things are. Okay, each of them will have a analog in the optimal growth model that we're going to talk about next week. And then basically the way we've couched this discussion is the following. A planner, whether it is a household or a benevolent social planner in the context of an economic model, is going to be confronted with a infinite horizon sequence problem. There's some infinite horizon utility maximization problem subject to constraints that a planner is going to have to solve. Those problems are difficult to work with analytically. And so the strategy in macroeconomics is a lot of times to transform those problems into something that is more manageable. Okay, that's what dynamic programming is all about. It's transforming an infinite dimensional sequence problem into really what is more or less a two-period functional equation or a Bellman equation, where you're trying to identify the optimal policy function and the value function rather than identify this countably infinite set of controls over time. Okay, in order to do that, however, we need to be certain that the Bellman equation or the solutions to the Bellman equation correspond to the solutions to the sequence problem that our planner faces. And that was really what this whole discussion was about. And to do that, we want to work through several of these theorems that establish equivalency between those two types of problems. There's also a handful of theorems in here that establish various properties of the value function that we're going to talk about today that will prove useful in future classes. And so that's what we set about doing, was establishing the various assumptions that were needed in order to establish the corresponding dynamic programming theorems. Okay. Now, how far did we get in the last class? We basically just went through theorems 1 and 2. Theorem 1 was the equivalence of values, right? Which was this idea that if we've identified the maximum value of the sequence problem, that will also attain the maximum of the Bellman equation, and vice versa, right? The second theorem was even more important, what your textbook author refers to as the principle of optimality, stating that if we've identified a sequence of controls or a plan, let's call it X star, that achieves the maximum of the sequence problem, then that value function, V star, can be broken into two components. The optimal value of the current return, U, plus the discounted optimized continuation return, beta times V star, where the state variable would be next period's control. Given the equivalence then between the value functions for the sequence problem and the Bellman equation, then that solution also has to be a solution to the functional equation, and vice versa, right? If we find an optimal policy or plan that maximizes the Bellman equation, it also achieves the highest value for the sequence problem. So trying to work with the functional equation is okay in the sense that we're not going to risk excluding the right solutions to the sequence problem, that the solutions to those two problems are going to coincide with one another. And really the only assumption that we needed to establish those two theorems, if you recall, was what? that the constraint correspondence, this menu of options that is available for the planner in choosing the control, is non-empty, that there has to be some well-defined set of options for the control, and that the overall objective function had to exist and be finite, right? The infinite sum of discounted payoffs had to be a finite number. That was all that was really required in order to establish theorems 1 and 2. Theorem 3 is important because it establishes the existence and uniqueness of the Bellman equation. Actually, did we talk about theorem 3 in the last class? Where did we finish? Just on theorem 2? Okay. All right, so to establish theorem 3, then, we need to go back and make a couple more assumptions about the underlying problem, okay? Particularly about the state vector, or the space that the state vector lives on. So assumption 2 looks like the following. So this capital X variable, that's the space that the control vector lives on. This is a compact, assumed to be a compact subset of RK. G, the constraint set, is assumed to be non-empty value, compact valued, and continuous. So we've already talked about G being non-empty, but it's also compact valued, meaning that for any value of X, the menu of possible X primes has to be a compact set. And G is also continuous, meaning that if we change X by just a little bit, the set of possible values for X prime also changes by just a little bit, right? So it doesn't have the same concept as a continuous function, but it is a continuous mapping. The utility function, or the payoff function, is also assumed to be continuous, and it maps elements of what I call X bar G into the reals, where X bar G is defined as the set of all X prime pairs that are on X times X, such that X prime is feasible. That is, it lives inside G of X. So X bar G is the set of all possible values of the state and control that are feasible, okay? Now, if G is compact valued and continuous, then that means X bar G is also going to be a compact set. Now, what does that mean about U? U is a continuous function defined on a compact domain. What does that imply about U then? That U is bounded. Any continuous function that is defined on a compact domain is going to be bounded. That assumption about U being bounded helps establish assumption 1, by the way, which says that the overall objective function has to be finite, right? The overall objective function is just the infinite sum of period utility functions discounted over time. So if U is bounded, it should bound the overall objective function as well. Now let me take a step back for a second and talk about what I mean by a compact set. You guys know what that is? Any
question?
Yes, it's a set that is, so when we're talking about Euclidean space, which is what we're talking about here, then X being compact means that it's both closed and bounded. That's all that really means, okay? I think it's the Hein-Borel theorem that establishes the fact that compact subsets of finite dimensional Euclidean space have to be closed and bounded sets. So for example, if we're talking about just the real line, then the closed interval A, B is a compact set. Okay, that's what I want you guys to think about here. If the capital stock, for instance, is our relevant state variable in the growth model, then the capital stock has to reside on a closed and bounded set. We know it can't be less than 0, so we've got the A part, but is there a upper bound on what capital can be in the model, so that without loss of generality, we can bound capital to some closed and bounded set? More on that next week. Okay, you guys understand the interpretation here? So X is compact, meaning it's closed and bounded. U is a continuous function on a compact domain, and so U is also going to be bounded. That's how I would interpret assumption 2. If we're willing to make assumption 2 regarding our infinite horizon problem, then we immediately can establish theorem 3. I'm not going to prove theorem 3, that's in your textbook, but we'll just talk about what it says. This is what your textbook author refers to as existence of solutions. Suppose that assumption 1 and 2 hold. Then there exists a unique, continuous, and bounded function, call it V, that maps elements from big X into the reals, that satisfies the following equation. V of little x is equal to max x prime on G, U x prime plus beta V x prime for all x in big X. Moreover, for any initial x on x bar, an or some optimal plan, let's call it x bar prime, exists. That's theorem 3 on the existence of solutions. So if assumptions 1 and 2 hold, then we have enough information to establish that there has to exist a unique, continuous, and bounded value function V that satisfies our relevant functional equation or Bellman equation. In other words, what this theorem does is it establishes the existence and uniqueness of the Bellman equation. Moreover, regardless of what the initial value of the state variable is, the model or the problem has some optimal plan to it. Now, there could be more than one. This theorem does not establish the uniqueness of X star. It just says that some optimal plan exists. Okay? What do we need to do to strengthen this maximization problem in order to guarantee the existence of a unique solution to the maximization problem? The second order condition needs to be satisfied. In other words, the maximization problem needs to satisfy some type of strict concavity requirement. Okay? And since it's V that we're maximizing, we need to establish the concavity of V. If we're willing to make the assumptions necessary for V to be strictly concave, then in fact a unique solution to this problem exists and can be represented as this time invariant policy function that we're in search of. But we need to go a little bit further with our assumptions. Theorem 3 just says that solutions exist, but they could be more than one. The Bellman equation, however, is unique and continuous and bounded. So combined with theorem 1, then, this theorem 3 implies that some set of optimal policies, perhaps a unique one, achieve not only the maximum of the Bellman equation, V, but also the maximum of the sequence problem, that is V star, given the equivalency between V and V star. Okay? Let me jump back over to my assumptions for a moment. Go to assumption 3. This assumption has two parts. One is that the period payoff function U is concave. Okay, what does that mean? Well, in order to establish that U is concave, one needs to show, and we're going to assume that it is, but in the context of the growth model, we're going to have to show that the payoff function is indeed concave. Concavity requires that for any alpha, let's say, between 0 and 1, and for any pair of points, x, x prime, and let's call it, x hat prime, where these points are in x bar G, that is the feasible domain of pairs x, x prime. U being concave implies that the utility function or the payoff function evaluated at the linear combination of these 2 points. So that is alpha x plus 1 minus alpha x hat, comma, alpha x prime plus 1 minus alpha x hat prime has to be greater than or equal to the linear combination of the payoffs evaluated at each 2 points. So that's alpha U of x, x prime plus 1 minus alpha U x hat prime. So concavity requires that this be true, that the payoff function evaluated at this linear combination of these 2 points, x and x hat, is bigger than the same linear combination of the payoff function evaluated at the 2 points separately. Okay. Now, as long as x is not exactly equal to x hat, then we can say that this is a strict inequality and that the utility function or the payoff function is strictly concave. That'll be the relevant case for us. All right, so U of alpha plus 1 minus alpha is bigger than alpha U plus 1 minus alpha U. That's the first part of assumption. There's actually another equally as important part, and that is that the constraint correspondence, G, must be convex. So U has to be concave, but G has to be convex. You guys know what it means for a set to be convex?
Like no holes.
Yeah, so in Euclidean space, if you take 2 points inside of a set, then all the points on the line segment connecting those 2 points also have to reside inside of the set, right? Mathematically, we say that for any, let's say for any alpha between 0 and 1, closed interval, and any x, x prime, x hat prime on big X, such that x prime is in G of X and x hat prime is in G of X hat, then you can show the following. The linear combination between x prime and x hat prime has to live inside of the set defined by the linear combination of x and x hat. not only must the payoff function be concave, but the constraint correspondence has to be convex. These are, by the way, very common assumptions made in economic applications. Whether you talk about it much in your micro class or not, all of those maximization problems that you do in application and in micro, to the best of my knowledge, feature concave preferences and convex budget sets. That will be true in this class as well. Okay? Let me just put this on. I think I've got enough room on this paper. Let me jump back to the next relevant theorem then, and that is Theorem 4, which we'll just call concavity of the value function. Let's suppose that assumptions 1, 2, and 3 now hold. So importantly, the utility, the payoff function is concave, the constraint set G is convex. Then the unique value function V that is identified in Theorem 3 that satisfies this Bellman equation that I wrote up here, mapping elements of X into the reals, is strictly concave. This, of course, follows naturally from assumption 3. The value function is the maximized value of the sum of all these period payoffs. If the period payoffs are concave, it stands to reason that the value function will also be strictly concave. Establishing Theorem 4 is important because it allows us then to ensure the existence of a unique optimal plan to the sequence problem and therefore the Bellman equation, which is the subject of, I believe it's a corollary in your notes called existence of optimal policy function. So we already know that the value function, that the Bellman equation is continuous and bounded and unique. We've now established the fact that the value function is strictly concave. That should be sufficient to guarantee the existence of a unique optimal plan that achieves the maximum of the Bellman equation. Okay, so if assumptions 1, 2, and 3 hold, then there exists a unique optimal plan. We'll call it X bar star, which is again some element of all these feasible sequence of X's over time. For any initial X. So if the value function is strictly concave, then there exists a unique optimal plan that achieves the maximum value of the Bellman equation for any potential initial value. Now here's the important part of this corollary. This optimal plan can be expressed as what's called a policy function. So for instance, the optimal value of xt plus 1, call it xt plus 1 star, can be written as some time invariant policy function pi of the value of X at date t, right? Where pi maps elements of X into X. It is the time invariant continuous policy function. So instead of trying to characterize this infinite sequence of X's over time, we can fully characterize that optimal plan using this time invariant policy function, meaning that the way x99 determines x100 is the same way that x3 determines x4, right? For instance, what if the policy function were the square root function, right? Then this would say that x2 is just the square root of x1. Well, x100 is just the square root of x99, right? That mapping from xt to xt plus 1 is the same for all t. That's what we mean by time invariant policy function. Okay. We have now established the basic theorems that are central for using dynamic programming as a mathematical tool to solve these types of problems. The last couple of theorems that I want to talk about for a few minutes here are really more about establishing some useful properties of the value function that we're going to appeal to when we're trying to prove certain properties of the optimal growth model next week. In particular, the things like the existence and uniqueness of the steady state in the optimal growth model. We'll come back and use these particular dynamic programming theorems. The stability of the steady state is another one. Does the steady state exhibit, this nice property of monotonic convergence? In order to establish those things, we have to know certain things about the value function in the representative agent model. One of them is that the value function is strictly increasing or monotonic. And the other useful one, obviously, is that the value function is differentiable, okay? The last one is easy to show and follows straight from the assumption that the utility function is differentiable. But let me talk about the monotonicity of the value function. That requires a different assumption. That requires the following, that the underlying, the period payoff function be strictly increasing in the state, and it requires that the constraint set G be something called monotone. Let me talk about both of those. So assumption 4 says that for each x prime in big X, u of x prime is strictly increasing in its first k arguments. Remember, x has dimension k. So what we're saying there is that if we increase the state vector x, we increase the payoff function u. Now, I'm not writing this as derivatives yet because we haven't established the differentiability argument here. But we're just going to say that u is strictly increasing in the state vector x. And that, if you think about this in terms of the growth model, that makes sense, right? What happens if the capital stock in period t rises? Then we produce more output. And if we produce more output, we get more consumption. And if we get more consumption, what happens to our utility? It goes up. So it's natural to think about increases in the state ultimately raising your utility, okay? So u is strictly increasing in x, or its first k arguments. But the other part of this assumption is that g is what's called monotone. Anybody know what it means to be a monotone mapping? So not a monotone function is one that is either non-decreasing or non-increasing, right? What is a monotone mapping? Remember, G is not a function. In what sense do we say that it is monotone?
It is one increasing, for some it's increasing, but it has the same value for some here.
Well, for every value of x, G gives us a compact set of possible x primes to choose. That set, right, is monotone if as we increase x, the set of possible x primes gets bigger and encompasses the previous one, right? So to define this mathematically, we would say, let's take an x that is less than or equal to an x hat. G is monotone implies then that G of x is fully contained as a subset of G of x hat, right? So let's say the capital stock today is 3 units. And given that value of the capital stock, the planner can choose KT plus 1 anywhere from 0 to 4. G would be monotone here if we increased KT to, let's say, 3.5. If that increased the set of possible values of KT plus 1, let's say from 0 to 7 or whatever, it's got to be a bigger set. So what a monotone mapping is here for this constraint correspondence is it basically kind of relaxes the constraints on the planner as we raise the value of the state vector, right? In other words, increasing the state relaxes the constraint that the planner faces to some extent. Higher values of capital at the beginning of the period give the planner a larger number of options to choose from when making a decision about capital for the next period. Both of those are important for establishing the next theorem, and that is Theorem 5. Which is what we call monotonicity of the value function. All right, let's suppose that assumptions 1, 2, and 4 hold this time in particular. And we're going to let V, again, be the unique, continuous, and bounded value function that satisfies that Bellman equation I wrote down on the last sheet, right? So V is this thing. Then as long as assumption 4 holds, as well as the other ones we've talked about, then V is strictly increasing in X. That is all of its arguments. So increasing the state is going to increase the planner's value function, which is the indirect utility, if you will, of pursuing an optimal plan over time. If the value function in the optimal growth model depends on the initial capital stock, that's the X, then what this is saying is that if our creator endows us with more capital in the initial period, the value function is going to be greater. We're going to achieve a higher level of total lifetime utility as a result of that. Not too surprising, right? But the monotonicity of the value function is really essential in establishing properties about existence, uniqueness, and stability of the steady state in the optimal growth model. All right, how are we doing so far? Everybody good? Okay. I tend to get lost in my discussion here because I've got like my assumptions written out and then the theorems, but then I'm bouncing back and forth. So I just talked about assumption 4, right? Where did that one go? Okay. Move to assumption 5. So by the way, I know this is kind of a dry discussion, right? But my goal here is for you guys to understand these dynamic programming concepts. And by the end of this, I want you to be able to use the theorems and the tools correctly to analyze dynamic macroeconomic models. Okay, so that's really the goal here, is for you guys to have kind of a practitioner's understanding of how to take a sequence problem, transform it into a Bellman equation, and then work directly with that Bellman equation to find solutions. Okay, to do that, you need to really understand what these theorems are actually saying. Assumption 5 is pretty straightforward. We're just going to make an assumption about U in that it's continuously differentiable in the interior of its domain, that is, in the interior of X bar G. This is not a controversial assumption, right? I mean, in all of these economic applications, we want to be able to use differential calculus to characterize the solution, the maximization problems, so that we can, appeal to first and second order conditions. That'll be the same here. If we're willing to simply make the assumption that the instantaneous payoff is continuously differentiable, then that is enough to establish the differentiability of the value function itself. That is Theorem 6. So let's suppose again that assumptions 1, 2, 3, 4, and now 5 hold. And we're going to remember what pi is. Pi is the optimal policy function defined in that corollary, which, if followed over time, achieves the maximum of the Bellman equation. And let's also assume that X is in the interior of its domain. So we're not talking about corner solutions here. And that pi of X is in the interior of its domain, which would be G of X, right? Pi of X tells us what the optimal value of next period's state is going to be. That is today's control. If these things are true, then the value function is itself differentiable. Okay? And the important part for us is that we can take the derivative then of the value function with respect to the state and appeal to something called the envelope condition. Okay? Now remember what the value function looks like. V of X is equal to the maximum of X prime on G of U X X prime plus beta V X prime. It's defined recursively in the sense that the value function itself depends on the value function. Now, if X prime can be written as an optimal policy function, pi of X, then what is V of X equal to? It's U of X pi of X plus beta V X prime. Well, what's the optimal value of X prime? That's just given by the policy function, pi of X, right? Now, what Theorem 6 tells us then is that we can find the derivative of V with respect to the state. That is the full gradient of V. So that upside down triangle, I think that's the gradient vector, right? What should that be equal to if we appeal to the envelope condition? You guys remember what that is? Have we talked about the envelope condition in this class? No? Have you covered it in math or in micro?
Yeah, we did it in both cases.
What's the envelope condition?
So essentially, you use it to, like if you get the optimal function,
Mm-hmm.
then you use it to see how that the particular variable changes if there's a change in an exogenous variable.
Perfect. X is an exogenous variable. V is the optimized function, right? What's the derivative of V with respect to X? Well, what the envelope condition allows you to do is differentiate the maximand by ignoring how the endogenous thing that you've maximized over depends on the state. In other words, I don't have to do a bunch of chain rule arguments here that would be, you know, the derivative of u with respect to the second argument times pi prime of x. I can ignore all those chain rule arguments, and this becomes just the gradient of u with respect to the first k elements evaluated at x and pi of x. And that's it, right? Because here, x only enters the value function in the next period through pi. Why can we ignore in this derivative all of the pi of x terms? Because if we were actually to take those derivatives, which we could, we would find that they cancel out because of the first order condition to this problem, right? So those pi prime of x terms, if you group them, you're going to find that they equal 0 because of the first order necessary condition of this maximization problem. We're going to come back to this in a few minutes, okay? But that's what the envelope theorem or the envelope condition it does. And so in these dynamic macro problems, when you write down the Bellman equation, the first things that you're going to be looking for are the first order necessary conditions and the envelope conditions. Together, those two things are going to help characterize the solution to the problem. Okay, Theorem 6 establishes that we can use the envelope condition here because the value function itself is differentiable. If we want to use differential calculus to characterize the solution to these problems, then we have to know from more primitive arguments that V itself is differentiable, because V is on the right-hand side of the thing that we're trying to maximize. Right? And so when we take the first order condition, we have to be sure that we can actually differentiate V with respect to the control. That's what Theorem 6 establishes, is that V itself is differentiable, and we can evaluate it using the envelope condition. And it follows directly from the differentiability of the payoff function U. Okay. Any questions so far? Don't worry, you guys will all be experts on this before the end of the semester. You will be able to write Bellman equations in your sleep. That's all you'll be seeing. You'll walk around and see Bellman equation and Bellman equation. All right, let me spend the rest of class today and perhaps a little bit of the next talking about the basic application of dynamic programming. Okay, so the goal then of the rest of the lecture is to show how the dynamic first order equations, what I've sometimes referred to as the Euler equations, together with another condition that hopefully I'll get to start talking about today called the Transversality Condition, are sufficient to characterize the solutions to these dynamic optimization problems. Okay, here's the setup. Let's suppose I've given you a sequence problem to solve. We're going to assume here that all of the assumptions necessary to establish equivalency between that sequence problem and the recursive formulation, that is the Bellman equation, are satisfied. So instead of solving the sequence problem, you immediately write down the Bellman equation. The Bellman equation is the following. The value of pursuing an optimal policy over time as a function of the state x is equal to the maximized value over the policy function x prime, which has to be an element of the constraint correspondence G, that's the relevant constraint here, is the sum of the current return plus the discounted continuation return. Now, we already know here that V is differentiable and that it is strictly concave from the various theorems that we've talked about. So if there is an interior solution to this problem, that is an x prime that's on the interior of the constraint set G, then the first order necessary conditions are both necessary and sufficient, right? We don't really have to do second order conditions because we know V itself is concave. So whatever value of x prime satisfies the first order condition will also satisfy the second order condition. Okay, so how do we proceed? This is a maximization problem. It's a weird looking maximization problem because the thing we're maximizing over has the value of the maximand in it itself. That's what I mean by it being defined recursively. But all of these concepts here, or quantities, are differentiable. So we should be able to take the first order condition. What are the set of first order conditions or Euler equations for this problem? Well, x prime is here and it's also here, right? So this would be the gradient then with respect to the second argument, x prime plus beta times the full gradient vector of the value function evaluated at x prime. Now, if we have identified an optimal policy function, let's call it an x prime star, right? That's my pi of x. Then this equation evaluated at x prime star should be equal to 0, right? That's the first order necessary condition. It's also sufficient because V is strictly concave. Does everybody understand the notation here? Now, X is a k-dimensional object, so there are really k first order conditions, right? Not just one. Okay, in your regular old calculus class, if you were confronted with a constrained maximization problem that you knew was strictly concave, then you could solve for the extremum point just from the first order conditions alone, right? That would be enough to solve, in this case, for x prime star. Why can't we solve for x prime star directly from these first order conditions here? What's the problem with this setup? What makes it difficult? Why can we not get x prime star directly from the first order conditions? The boy?
Yeah, we don't have an explicit functional form for it.
Well, okay, even if we knew what the functional form for u was, what do we not know yet? We don't know V, because V depends on first knowing what x prime star is, right? So that's the problem here, is that we've got an unknown function V on the right-hand side. Well, is there a way that we can somehow get rid of this unknown value function argument on the right-hand side to express it in terms of only things that we do know? Yes, but we have to appeal to the envelope condition. What's the envelope condition on this problem? The gradient of V with respect to x was equal to what? The gradient of u with respect to the first argument of x pi of x, or x prime star. how can we use this information here to substitute it into the first order condition so that we have an equation that only depends on utility arguments? The first order condition has the gradient of v evaluated at x prime. The envelope condition has the gradient of v evaluated at x. So what we have to do here is something a little clever. We have to scroll forward the envelope condition. The gradient of v evaluated at x prime then should be equal to the gradient of u with respect to the first argument evaluated at x prime, and then let's call it x double prime. That is x 2 periods ahead. Right? Well, what's the right-hand side look like? X prime is, of course, just pi of x, right? What is x double prime? That would be pi of x prime, right? Well, what would pi of x prime be? That's like pi of x. So we can take that information and substitute it into the first order condition to get the gradient with respect to the second argument, u of x pi of x, plus beta times the gradient of the value function evaluated at x prime star. Well, that's just the gradient of the utility function with respect to the first argument evaluated at pi of x comma pi of x. That is equal to 0. These are the Euler equations of the model. And we've eliminated the unknown value function from the first order condition. Now, unfortunately, we still can't solve this equation directly using standard methods. Why? We're not so much looking for a value of x prime as it is we're looking for a policy function, right? So this is still a functional equation, but this time in the unknown policy function rather than the unknown value function. Functional equations are hard to solve numerically and analytically. There's only a certain class of problems that you can actually solve analytically. Of course, those will be the ones that we do in class because you could solve them with pencil and paper. And so in the next section of the course, I'll show you guys some techniques on how to do that. One of the most common techniques to solve functional equations is what's called the method of undetermined coefficients. You guys heard of that before or used it? That's where you essentially guess a form of the policy function pi, and then you substitute that guess into your first order conditions, and then you match what are called the undetermined coefficients until you get a solution. As long as you make the correct guess, you can solve for the policy function. So there is a class of optimal growth models. Usually it has logarithmic preferences and things like Cobb-Douglas production that are solvable analytically using a guess and verify strategy. But these are going to require these other types of solution techniques to work with, which we'll get to in the next week. Okay, you guys are kind of scratching your heads here. You look a little confused. So I think the result becomes simpler if we consider a special case. What if we consider the case in which x is just a scalar? So x prime just lives on the real line. Okay, so v of x is just the max of x prime on G. Let's see, u of x, x prime, plus beta v x prime. Well, if x is a scalar, then we can just take derivatives in the usual way without using this clumsy gradient notation. It would be what? The partial of u with respect to x prime, or the second argument, plus beta v prime of x prime is equal to 0. That holds at the optimal value of x prime. What do we know x prime star is equal to? Because of the corollary, we know that it takes the form of a time invariant policy function. And so, well, let me do one more step. We need a value, we need an envelope condition here too, right? What is v prime of x? V prime of x is the partial of u with respect to the first argument evaluated at the optimal value of x prime, which is just the partial of u x pi of x with respect to the first argument. We can then rewrite the Euler equation as partial of u x pi of x with respect to the second argument plus beta times the partial of u, let's say pi of x pi of x with respect to the first argument is equal to 0. Just rework the problem in this case, in the scalar case. The Euler equation has a straightforward interpretation. Okay, what's the first term here? That shows the marginal utility value of increasing the control today by 1 unit, right? What's the other part? It's the discounted continuation value of having a higher control starting in the next period. So again, let's couch this in terms of the growth model. What's the control? Remember what I showed you in the last class? The control is kt plus 1, right? What would the first term be? If we increase kt plus 1, what happens to consumption at date t? It goes down, right? More capital that you carry requires more investment. And so consumption is going to decline today. And so what happens to your utility today? It's going to go down a little bit since it depends on consumption. So the marginal utility loss from increasing your savings today would be this du dx prime or du dkt plus 1. But there's a benefit to having greater capital, right? Next period, if you have greater capital, you're going to be able to produce more and therefore consume more. The other part is the discounted continuation return of having that additional resource next period and for the rest of your life. What does this equation say? That the marginal cost of lowering consumption by $1 today plus the discounted value of having $1 more worth of resources starting tomorrow and going forward has to be equal to 0. In other words, the value of shifting $1 intertemporally from the future into the present or from the present into the future has to be 0. And that should make sense, right? If indeed we've identified an optimal policy We should not be able to rearrange resources intertemporally in a way that raises our lifetime utility. We should be on that smooth, optimal consumption path over time. If I was able to save an extra dollar today and consume the returns to that saving tomorrow, and that raises my lifetime utility, I'm not behaving optimally, right? The marginal cost of lowering consumption today should be exactly equal to the marginal benefit of the higher consumption you get in the future. Only when that is true and that equation is equal to zero are you behaving optimally over time. That's kind of the interpretation of this dynamic Euler equation, right? The sum of the marginal utility value of increasing the control today and the discounted value of having a higher control tomorrow forever should be equal to zero. Or alternatively, if we impose the time subscripts back into the problem, just to make this more explicit, the derivative of u with respect to xt plus 1 plus the discounted value of the partial of u evaluated at xt plus 1 and xt plus 2 with respect to xt plus 1 is equal to 0. That must be true for all values of t. This is a popular representation of the Euler equation. It has the time subscripts back in there. So if xt is the capital stock, raising the capital stock for next period lowers your current utility because it lowers consumption, but you gain future utility because you're saving that resource. You're able to produce more goods and services next year, earn a return on that is, and consume more in future periods. The sum of those two things, the marginal cost and the marginal benefit, should sum to 0. Okay, let me just introduce the final concept that we're going to talk about, and I will finish my discussion of this on Monday. And then I'm not going to do a proof of Theorem 7. It's more of just kind of a heuristic illustration of why it has to hold. But the other criteria that you all need to worry about here when confronted with a sequence problem that you transform into a Bellman equation, and then you write the first order condition and you get the envelope condition, and you combine those two to give you the Euler equations that we've just talked about. The Euler equations are necessary, but they're not sufficient to fully characterize an optimal solution or optimal plan to the underlying sequence problem. There's one other condition that must be satisfied by an optimal plan or an optimal sequence of x's in this family of problems. And that is this thing called a transversality condition. You can think about a transversality condition as corresponding to a terminal value condition in a problem that has an infinite horizon. Okay, you know, in differential equations where you guys have taken your diffie-q class where you have, it's been many, many years since I took one, but I recall that characterizing the solution to differential equations sometimes involves pinning down boundary conditions, initial conditions, or terminal conditions. This is something similar to that. Okay, in an infinite horizon problem, there's one other kind of terminal value condition that must be satisfied in order for the policy to achieve the maximum of the dynamic program. In other words, it's not, even if you've identified an X star that satisfies the Euler equations, it might not actually achieve the maximum of the Bellman equation unless it also satisfies the transversality condition, this terminal value condition. What I'm going to do today is just write down the transversality condition and interpret it. And then for the first 20 or 30 minutes of the next class, we'll go through it's not a formal proof, but a description of how to motivate the transversality condition from a finite horizon model. So imagine that instead of an infinite horizon problem, we have a finite horizon problem where the last period, capital T, is way out into the future. You can actually get a sense about what the transversality condition is by thinking about what the first order condition looks like for the very last value of x, like x cap t plus 1. And then if we take t to the limit to infinity, you basically get something that is identical to the transversality condition. So I'm going to motivate the existence of this transversality condition by appealing to a finite horizon setup to give you some intuition about kind of where it comes from. Now, with all of that said, let me emphasize that the transversality condition is hugely important for the class of models that we're going to talk about, okay? In particular, the neoclassical growth model that we're going to study after we talk about the optimal growth model. In order to prove the existence and uniqueness of an equilibrium path that goes to the steady state in that model, we're going to have to appeal to the transversality condition. In other words, without the transversality condition, you can't even guarantee the existence of a stable path to the steady state. Like in the solo model, there's just that one path that goes from the initial point to the steady state. In the neoclassical growth model, there are an infinite number of possible stable paths to the steady state. To rule out all of them but one, so that we have a unique solution to the model, you have to appeal to the transversality condition. And it's going to be intimately tied to this concept of a lifetime budget constraint for a representative household that lives forever. Okay, so while this may seem esoteric and irrelevant at this point, that, you know, the Bellman equation and the first order condition and the envelope condition seem like the most important thing, and they are important. The transversality condition is also really, really important for this class of models. And so we need to, it's important that you guys understand where it comes from, and to be able to write down the correct transversality condition for a problem that I might present you. Okay, here's what the transversality condition looks like in the general model that we've talked about. The limit as t goes to infinity of the discounted value, so beta to the t, times the marginal value of the state. So the gradient of u with respect to the first argument times, or I should say inner product, since these are vectors after all, is equal to 0. This is the transversality condition. You need to kind of commit that to memory and be able to write down the transversality condition for a problem that you might see on an exam or a homework. Okay, what does it mean? So the gradient with respect to the first argument is the marginal value of the state, xt, right? Times, or inner product, the state. This product here has to not get bigger at a rate that is faster than beta inverse, so that the product of these two things limits to 0. So the discounted value of the optimal marginal value of the state has to go to 0 as time goes to infinity. That's what the transversality condition says. Now let me try to interpret that for you. If we go back to our Euler equation, what does the Euler equation say? That tells us that we should not be able to shift resources intertemporally in a way that raises our lifetime utility, right? If I save an extra $1 today, I shouldn't be able to raise my lifetime utility by consuming that extra $1 in the next period. In other words, what the Euler equations tell us is basically what the optimal slope of the consumption trajectory is over time, okay? The transversality condition is something different. It tells us basically what the trajectory of that overall consumption profile should be. In other words, we should not be able to change simultaneously a bunch of values of X over time in a way that raises lifetime utility. So whereas the Euler equations are about achieving the optimal slope of the consumption trajectory over time, I can't rearrange my consumption between periods t and t+1 in a way that raises lifetime utility. Satisfying the transversality condition is equivalent to saying I can't simultaneously change C1, C2, C3 on out to C infinity in a way that raises my lifetime utility. So it's an infinite number of changes in your control vector over time. You can't, if you're behaving optimally, you shouldn't be able to make those changes and improve lifetime utility. That is equivalent to a condition like this holding, that the marginal value of the state evaluated at our presumed optimal plan limits to 0 at infinity, or the discounted value of the marginal value of the state. Okay, I'm going to stop there. Again, what I'm going to do in the next class is try to motivate the existence of this. That is, why must this hold for an optimal policy X star from the perspective of a finite horizon model? And that is basically the subject of Theorem 7. So that what Theorem 7 says is that if all of the assumptions that we've talked about are satisfied, then we only need 2 pieces of information to characterize an optimal solution to these dynamic programming problems. One is the intertemporal Euler equation, and the second is the transversality condition. As a practitioner of dynamic programming, that's all you need to be able to do, is take a sequence problem, transform it, or give it its recursive representation, that is, write the Bellman equation, and from the Bellman equation, derive the intertemporal Euler equations and the transversality condition. Those 2 objects fully characterize the solution to an infinite horizon sequence problem under all of those assumptions that we've talked about. Okay, if you can do that, you are what I would call a good practitioner of dynamic programming and can analyze the infinite horizon growth models that we're going to talk about for the remainder of the semester. Okay, you guys have any last questions then about that before we stop? That should take maybe 20 minutes or so of the next class, and then we're going to move directly into the optimal growth model after that. So we will apply all of these dynamic programming theorems to the infinite horizon representative agent model.